Here's the question. Why does time only go forward? Think about it. Really think. You drop a glass, it shatters. You've never, not once, seen shattered glass pieces leap up off the floor, assemble themselves perfectly, and fly back into your hand. Never. Not in a billion years of watching. But here's the terrifying thing, the fundamental laws of physics. Every single one of them works perfectly well in reverse. The equations don't care. Gravity works backwards. Electromagnetism works backwards. Quantum mechanics backwards. Every single law of nature at the microscopic level is completely, utterly, embarrassingly time symmetric. So where does the arrow of time come from? Why do you feel it? Why does your memory go one direction and not the other? Why do you age forward? Why does the universe seem to insist violently, relentlessly, on moving from organized to chaotic? Going to tell you exactly why entropy doesn't just measure disorder. It is time. It creates time. It is the reason you feel like you're moving forward through existence rather than floating in an eternal, directionless now. Buckle up. This is going to shake you. What is entropy, really? Feynman moves to the chalkboard, writes, S equals K log W, underlines the W. Before we talk about what entropy is, let me tell you what most people think it is, because the popular version, the version your high school teacher probably told you, is close enough to be dangerous. They tell you entropy is disorder. Things go from order to disorder. Your desk gets messy. Your coffee gets cold. Eggs break. That's entropy, right? Well, sort of. But that version is like saying electricity is the stuff that makes your toaster work. It's true, technically, but it completely misses the soul of what's happening. Let me back up and start with a man named Ludwig Boltzmann, because without Boltzmann, we'd all be utterly lost. Boltzmann was one of the greatest physicists who ever lived, and here's the tragedy: he died not knowing if atoms were real. He spent his entire life fighting for the atomic theory of matter, being mocked, being dismissed, and eventually, in 1906, he took his own life. 2 years later, Einstein proved atoms were real, beyond any shadow of doubt. Boltzmann never got to see it. That's one of the saddest stories in science. But Boltzmann left us something magnificent. He left us a formula. It's carved into his tombstone in Vienna. The formula is S equals K log W. That's it. That's the whole thing. S is entropy, K is a tiny constant, Boltzmann's constant, and WW is the beautiful, shocking, revolutionary part. W is the number of ways you can arrange the microscopic pieces of a system to produce the same macroscopic appearance. Let me say that again more slowly, because it's the key to everything. Imagine a box. In the box, there are 100 molecules of gas. Now, the question is, how many different microscopic arrangements, how many different positions and velocities for each individual molecule would all look the same to you if you could only see the big picture? If all the molecules are crammed into the left half of the box, the number of arrangements that produce that situation is relatively small. The molecules have to be specifically, precisely over there. Not many ways to do it. But if the molecules are spread out roughly evenly through the whole box, the number of microscopic arrangements that produce that situation is absolutely astronomical, incomprehensibly large. Because molecule number one could be here or there or over there, and you'd never know the difference from looking at the big picture. That number W, the number of microscopic arrangements consistent with what you see as entropy. More precisely, entropy is proportional to the logarithm of that number. And the logarithm is in there because these numbers are so enormous that you need logarithms just to make them fit on the page. Now here's where it gets beautiful, and where time starts to whisper its secrets. If you start with a gas crammed into one corner, low W, low entropy, and you let it evolve, where does it go? It spreads out. Why? Not because there's some force pushing it, not because molecules are lazy, but simply because there are vastly, incomprehensibly, more arrangements that look spread out than arrangements that look crammed in the corner. When you pick a random arrangement from the astronomical number of all possible arrangements, you almost certainly get a spread out one. Not because of any law that pushes you there, just because that's where almost all the arrangements live. This is the second law of thermodynamics, and it's one of the most peculiar laws in all of physics, because it's not really a law in the traditional sense. It's a statistical inevitability. It's not that entropy must increase. It's that entropy almost certainly increases because there are so many more high entropy states than low entropy states that stumbling into a low entropy state by chance would be like winning the lottery 1 trillion times in a row. And now you're starting to see time. Because if entropy almost always increases, if systems almost always move from low W to high W, then entropy gives us something none of the other fundamental laws gave us, a direction. Entropy is the compass that points to the future, not because physics demands it, because mathematics makes it overwhelmingly probable. The arrow of time isn't written into the fabric of space-time by some decree of the universe. The arrow of time emerges from the stunning, breathtaking enormity of the number of possible arrangements of atoms. Think about how strange and beautiful that is. Time, the most intimate thing you experience, the river you swim in, every moment of your conscious life, emerges from counting, from statistics, from the simple, dumb fact that there are more messy arrangements than tidy ones. That should blow your mind. If it doesn't, you haven't understood it yet. But wait, we haven't addressed the really hard question, because all of this just pushes the mystery back one step. If entropy increases over time, and we observe entropy currently increasing, that means entropy was lower in the past, which means there was a time of extremely low entropy, a time of exquisite, improbable, astonishing order. When was that? How did it happen? And why did the universe start in a state of incomprehensibly low entropy? That question, the question of the initial conditions of the universe, is where things get truly mind-bending, and we'll get there. But first, let me make sure you feel in your gut exactly how entropy connects to what you call time. Why you can't remember tomorrow. Feynman sits on the edge of the stage. Conversational, almost confessional. Here's what I want you to do right now. I want you to make a memory. Think of something that happened to you yesterday. A meal, a conversation, something you saw. You remember it, right? There's a sense that it's in the past, that it happened before this moment. You feel completely certain of its pastness. But here's a question that will genuinely disturb you if you sit with it. How do you know? How do you know your memories are of real past events rather than, say, a detailed fiction that was built into your brain 5 minutes ago, complete with fake emotional resonance and false sense of familiarity? How do you know that the universe wasn't created 10 minutes ago, complete with all the fossils, all the geological strata, all the stars at exactly the distances they'd need to be for their light to have been traveling for billions of years, all of it placed ready-made into existence with your memories preloaded? You can't prove that didn't happen. You simply can't. And that's not a philosophical trick. That's a genuine epistemological cliff edge. But here's the physics of the thing. Your memories are physical. They're stored in patterns of neural connections, in the strengths of synapses, in the precise configuration of protein molecules in your neurons. Your memory is a physical record. And physical records, by the laws of thermodynamics, carry information about past entropy gradients. Let me explain what I mean by that, because it sounds complicated and it really isn't. When you take a photograph, what happens? Light from a scene, a specific configuration of photons hits a film or a digital sensor. That specific configuration causes a specific physical change in the recording medium. The record stores information about the past state of the light. For that record to be reliable, for the photograph to actually represent the scene you were trying to capture, you need something crucial. The photographic medium needs to start in a low entropy state. If you use a film that's already been randomly exposed, randomly jumbled at the molecular level, the new information from the incoming light can't be reliably recorded. There's too much existing noise. Memory works the same way. For your brain to record a reliable memory of an event, your neurons need to start in a relatively low entropy configuration that can be specifically altered by the event. The new information needs somewhere clean to land. And this means this is the breathtaking part. Your ability to have memories at all depends on entropy having been lower in the past than it is now. The existence of your past is not just a fact about time. It's a thermodynamic fact. You remember the past because entropy was lower then. And entropy was lower then because the universe started in an incredibly low entropy state. The direction of your memory, the fact that you remember yesterday and not tomorrow, is the same arrow as the thermodynamic arrow of time. They're not just correlated. They're the same phenomenon. You experience time flowing from past to future because entropy increases from past to future. Your sense of now moving forward, your sense of being carried along by time's river, that's what it feels like from the inside to be a physical system in a universe where entropy is increasing. Let me make this even more visceral. The reason you can't remember the future isn't because the future hasn't happened yet. It's because the future is a higher entropy state. In a higher entropy state, there are more possible microscopic arrangements. You can't make a reliable record of any single future state. because there are too many possible futures. The statistical weight is spread over an enormous number of possibilities. The past has already happened. The laws of physics and the specific history of the universe have selected a particular sequence of low entropy states leading up to right now. That's a specific, definite path. And you can keep records of specific, definite paths. The future hasn't been selected yet. From where you are right now, many futures are thermodynamically possible. Some are more likely than others, but they're all live options in a sense the past isn't. And you can't make a reliable record of something that hasn't been selected from among possibilities. This is why prediction and memory feel so different. Memory feels certain, rich, detailed, definite. Prediction feels uncertain, fuzzy, probabilistic. And that's not a limitation of your brain. That's thermodynamics. Now here's something that really ought to give you a sleepless night, because it bothered me for years. We've established that entropy gives time its direction. And we've established that the thermodynamic arrow of time is what creates memory, what creates causation, what creates the felt sense of temporal flow. Fine, great, wonderful. But the equations of physics, the actual mathematical laws, they don't have an arrow. They're reversible. Every process they describe can run forward or backward with equal mathematical validity. So where does the arrow come from? It comes from the boundary condition. It comes from the beginning. It comes from the fact that the universe was in an extraordinarily low entropy state at the Big Bang, but that just moves the mystery. Why was the Big Bang low entropy? Why wasn't it high entropy? If you generate a random state for the universe from among all possible states, you'd almost certainly get a high entropy one, a thermal equilibrium, a uniform soup of radiation and particles with no interesting structure. The low entropy initial state of our universe is, from a purely statistical standpoint, a staggeringly improbable conspiracy. This is what Roger Penrose calculated. The probability of the universe's initial state being as low entropy as it was is roughly 1 inch 10 to the power of 123. That's not a typo. It's a number so large that if you wrote a 0 for every atom in the visible universe, you wouldn't have enough atoms to write down that number. The universe was born in a state of almost incomprehensible improbability. And that improbability is the source of time's arrow. That improbability is the reason you experience time at all. Life, order, and the cosmic spring. Feynman stands, animated, arms moving as he describes molecule. I've been a teacher for most of my life, and I've learned one thing above all others. The best way to understand something is to watch it break. To find the cases where the rule doesn't hold, or almost doesn't hold, or holds for reasons you didn't expect. So let me show you a case where entropy does something so bizarre, so counterintuitive, that it seems to violate everything I just told you. Life. You, right now, reading this, you are a magnificently complex, beautifully ordered structure. You are patterns within patterns within patterns, molecules arranged into cells, cells arranged into tissues, tissues into organs, organs into a thinking, feeling, remembering creature who is actually sitting here being troubled by thermodynamics, which is remarkable in itself. If entropy always increases, if things always go from order to disorder, how in the world does something as ordered as you exist? How did a universe that started simple end up with galaxies and planets and trees and jazz and particle accelerators and quantum mechanics classes? This is where people sometimes think they found a flaw in thermodynamics. Creationists have used it. Vitalists have used it. People who don't understand physics, and some people who really should have pointed at life and said, see, entropy can't be right, life proves it. They're wrong. But the error is instructive, and fixing it will teach you something profound. The second law doesn't say entropy increases everywhere, all the time, unconditionally. It says entropy increases in isolated systems, systems that don't exchange energy or matter with their surroundings. And crucially, you are not an isolated system. You eat food. Food is a low entropy, highly organized chemical structure, complex molecules with lots of stored chemical energy, lots of structural information. You take that low entropy food, extract the energy and information from it, use it to maintain your own complex structure, and then excrete high entropy waste heat, carbon dioxide, metabolic byproducts. You are a machine that imports low entropy and exports high entropy. You locally decrease entropy at the cost of increasing it enormously in your surrounding. And where does the food's low entropy come from? Plants. Plants take sunlight photons of low entropy, coherent electromagnetic radiation from the sun and use it to build sugary, ordered molecular structures. And where does the sun's low entropy come from? Nuclear fusion, the burning of hydrogen into helium, which releases energy that was stored when the hydrogen was created in the Big Bang in a low entropy state. Follow the chain all the way back, and you always arrive at the same place: the extraordinarily low entropy of the early universe. The Big Bang is not just the source of matter and energy. It's the source of order. It's the source of the gradient that drives all processes, biological and chemical and geological, across the entire history of the cosmos. You are powered by the Big Bang. Your thoughts, your heartbeat, your consciousness, all of it is the universe's low initial entropy working its way up the thermodynamic gradient toward equilibrium. You are a temporary eddy of order in the cosmic flow from low entropy to high entropy. That's not depressing. That's magnificent. You're made of 13-billion-year-old low entropy. You're the universe knowing itself through a roundabout thermodynamic process. Now here's the subtlety that most textbooks completely miss, and it drives me absolutely crazy. When people say entropy is disorder, they're implying that disorder is somehow the natural state of affairs and order is the remarkable exception. But disorder is only disorder relative to some reference frame, some definition of what counts as organized. Consider a crystal, a perfect crystal of salt, sodium, and chlorine atoms arranged in a perfect lattice, every atom in its right place, stretching in 3 dimensions with absolutely regular periodicity. Is that ordered or disordered? Well, it's ordered, obviously. And its entropy is low. We all agree on that. Now consider the same atoms, but each one moving around randomly, filling a gas container, hitting each other and bouncing, with no pattern, no lattice, no organization. That's disordered. High entropy, okay? That's all consistent with the simple picture. But here's where it gets strange. Take a mixture of 2 different types of polymer molecules, long, complex chains of atoms. Under certain conditions, these polymers spontaneously arrange themselves into beautifully regular structures. Stripes, hexagons, spiral, intricate, gorgeous patterns that look for all the world like they violate entropy. But they don't, because the entropy of a system includes not just the positional entropy of the molecules, but also something called conformational entropy, the number of ways the flexible polymer chains can bend and fold and twist. When polymers segregate into patterns, they gain conformational freedom even as they lose positional freedom. The total entropy, properly counted, increases. And this happens in biology constantly. The folding of proteins, the self-assembly of cell membranes, the formation of DNA double helices. All of these look like local decreases in disorder, and they are in a crude sense, but they're all driven by entropy when you count all the degrees of freedom properly. This is a crucial lesson about entropy and time. The arrow of time isn't always visible in the obvious macroscopic changes you can see. Sometimes time's arrow manifests in ways that look like increasing order because entropy is being maximized in hidden degrees of freedom that you're not directly watching. The universe is always, always moving toward higher entropy, but higher entropy doesn't always look like a mess. Sometimes it looks like a crystal. Sometimes it looks like a snowflake. Sometimes it looks like a living cell. Sometimes it looks like you sitting here thinking these thoughts. The arrow of time is always there, always pointing forward, even when it's hiding. The block universe and the illusion of flow, Feynman pauses. His tone becomes quieter, more serious. Let me tell you about the most dangerous idea I ever encountered in physics. Not dangerous because it was wrong, dangerous because it was right. And the implications were so enormous that most people who encounter it spend years quietly going insane. The idea is this: from the fundamental laws of physics, the past and the future are equally real. That needs unpacking. Let me set it up properly. We have 2 completely different ways of talking about reality in physics. The first is classical, or relativistic, or quantum mechanics, the dynamical laws that tell you how things evolve, how the position and momentum of a particle at one moment determine its position and momentum at the next. These laws are time symmetric. They run equally well, forwards and backwards. The second is thermodynamics, the statistical behavior of large collections of things. And thermodynamics has an arrow. Now, here's the puzzle. If the underlying laws have no arrow, where does thermodynamics get its arrow from? We said it comes from the initial conditions from the Big Bang being low entropy. But that raises a deeper question. In a universe governed by time-symmetric laws, what does it even mean for one end of time to be initial and the other final? If I showed you a movie of the universe playing backward galaxies unforming, stars unshining, life dismantling itself, atoms spreading back into the primordial fireball, the fundamental laws of physics wouldn't object. That film would be physically valid. The only reason we call the Big Bang the beginning and call the future is because entropy is lower near the Big Bang. And we call the low entropy end the beginning because we remember it. And we remember it because our brains being physical systems that record information, thermodynamically record information in the direction of increasing entropy. So we call something the past because it's the low entropy direction. And our memories point in the low entropy direction because of thermodynamics. It's circular, beautifully, dizzyingly circular. And this brings us to a picture of time that is fundamentally different from the one you carry around in your gut. The physicist's view, the view I believe is closest to the truth, is that time is not flowing. The universe is not a film being played forward. The universe is more like a sculpture, a four-dimensional block of space-time with all moments existing simultaneously, each sliced moment equally real. This is what physicists call the block universe, or eternalist view of time. In the block universe, the past, present, and future all exist with equal ontological status. You at age 10 is just as real as you right now. You, 20 years from now, if you're lucky enough to exist, is just as real. All moments are laid out, crystallized in four-dimensional space-time. In the block universe, time doesn't flow. You flow through it. Or rather, the momentary you, the you slice at this particular moment, has memories of past slices and makes predictions about future slices. But the flowing sense of time, the felt sensation of now moving forward, that's something that happens inside the block, not something happening to it. The arrow of time in this picture isn't about time flowing in one direction. It's about the thermodynamic gradient being oriented a particular way in the block. The entropy increasing direction just is what we call the future, not because it's ontologically special, but because it's the direction our memories and records point. Now, does this mean free will is impossible? Does it mean the future is fixed? Does it mean your choices don't matter because they're already crystallized into the block? Careful, this is where people panic. First, quantum mechanics complicates the block universe picture significantly. The uncertainty principle, the measurement problem, the branching of wave functions, these introduce a genuine irreducibility into physics. That means the future might not be fully determined in the classical sense. The block might have multiple possible futures that exist in quantum superposition. But second, and more importantly, even in a completely deterministic block universe, your choices would still be real and meaningful. Your deliberation process is one of the physical processes that determines what ends up in the block. The fact that it's all fixed doesn't mean your reasoning doesn't matter. Your reasoning is one of the fixed things. It is part of the cause. I'm not going to pretend these questions are fully resolved. They're not. Philosophers and physicists have been wrestling with the block universe and free will and the nature of temporal experience for a century, and we don't have clean answers. But here's what I find extraordinary. These are not purely philosophical questions. They're questions that touch on real physics. The nature of time, the meaning of the arrow, the status of the past and future. These are things we can make empirical statements about. These are things we can measure and test and argue about with actual evidence. And the evidence, so far, points to a picture of time that is nothing like the intuitive river you carry in your gut. Time isn't flowing. Entropy is increasing. And those two facts together, entropy, increasing in a block universe where all moments are equally real, conspire to produce the exquisite illusion of temporal flow that you experience every waking moment of your life. The universe is playing a trick on you, a beautiful, elaborate, physically precise trick. And understanding the trick doesn't make it less beautiful, it makes it more. The embarrassing hole. Why did time start? Feynman sits, long pause, then leans forward. I want to talk about something that embarrasses physicists. Not because it's wrong, but because it's a hole, a real gaping, intellectually uncomfortable hole in our understanding of entropy and time that most textbooks paper over with soothing words and hope you don't notice. The hole is this. We don't know why the universe started with such incredibly low entropy. And without knowing that, we don't really know why time has an arrow. Let me be more precise about why this is so troubling. The argument for the arrow of time goes like this. Systems evolve from low entropy to high entropy because there are so many more high entropy states than low entropy states. Fine. But now ask, if that's true, why was the initial state low entropy? If you pick a random state for the universe from among all possible states, you'd expect to pick a high entropy state, because most states are high entropy states. So the low entropy initial state of our universe is either the result of some deeper physics that we don't yet understand, or it's a staggering coincidence, or it's something that requires anthropic reasoning to explain. Stephen Hawking and Roger Penrose thought deeply about this. Penrose proposed something he called the Weyl curvature hypothesis, the idea that there's some physical principle that suppresses the gravitational degrees of freedom at the beginning of the universe, enforcing a low entropy start. But this is speculative. We don't have a derivation of it from deeper principles. A completely different approach. Maybe the universe we live in is just one of infinitely many universes with different initial conditions. And we have to find ourselves in a low entropy one, because in high entropy universes, there would be no complexity, no planets, no life, no observers. This is the anthropic argument. And it makes some physicists deeply uncomfortable because it feels like cheating. Then there's Sean Carroll's picture, the idea that time is fundamentally symmetric, that the past and future are equally real, and that the low entropy Big Bang is just the low entropy end of a larger temporal structure that extends in both directions. In this picture, there might be another side to the Big Bang, another era of the universe in which entropy increases in the opposite temporal direction, where observers would call their past what we call our future. These are not idle speculations. These are serious proposals from serious physicists, and they have real mathematical structures behind them. But none of them is confirmed. None of them is the consensus. What is the consensus is that the low entropy of the Big Bang is a genuine mystery. It's not explained by general relativity. It's not explained by quantum mechanics. It's not explained by the standard model of particle physics. It's a fact about initial conditions that we accept but don't derive. And here's what makes this especially philosophically rich. The mystery of time's arrow reduces to the mystery of the initial conditions of the universe. Why does time go forward? Because entropy increases. Why does entropy increase? Because it started low. Why did it start low? We don't know. That's not a failure of science. That's science being honest. And honesty, even uncomfortable honesty, is the foundation of the enterprise. But let me offer you something that I find more personally satisfying than the speculative cosmological arguments. Let me offer you a different angle on why the low entropy of the past is remarkable. Think about what it means for a physical system to be complex. Complexity, the kind that produces interesting phenomena, life, intelligence. Technology requires BOTH, low entropy, and energy gradients. You need some parts of the system to be far from equilibrium relative to others. You need differences. You need gradients. A universe in thermal equilibrium, maximum entropy, no gradients, everything at the same temperature is a dead universe. It's called the heat death of the universe, and it's a real physical prediction. Eventually, in time so vast that they make the current age of the universe look like an eye blink, our universe will approach that state. Stars will burn out. Black holes will evaporate. The temperature will equalize across all of space-time, and nothing interesting will ever happen again. But right now, we live in the vast, unimaginably productive middle period. We live in a time when the entropy gradient, the difference between the low entropy of the sun and the high entropy of the cold, dark sky, drives an enormous, ongoing explosion of complexity. We live in a time when the low initial entropy of the Big Bang is still slowly unwinding, like a cosmic spring releasing its energy across billions of years. Consciousness, as far as we know, requires complexity. It requires information processing. It requires the constant flow of energy through ordered structures. All of that is thermodynamics. All of that is entropy. You are conscious because the universe is not yet in equilibrium. You are thinking because entropy hasn't finished increasing yet. Your awareness, this very sensation of being here, now, aware is a temporary thermodynamic phenomenon permitted by the fact that we're living in the middle of the greatest entropy increase in the history of the cosmos. And that's not sad. That's wonderful. You are one of the universe's most elaborate ways of converting low entropy into high entropy while doing something spectacularly interesting in the process. You are a thinking entropy machine. And for a brief, glorious cosmological moment, you're here to notice it. The most important thing I know. Feynman stands center stage. The lecture is winding to its close. His voice is warm. We've come a long way. Let me pull the threads together, because I think the full picture is even more extraordinary than any of the pieces. We started with a simple, seemingly philosophical question. Why does time feel like it moves in one direction? Why do you feel like you're being carried forward through moments from past to future, never backward? And we found through the work of Boltzmann and Clausius and Maxwell and dozens of others, and through the uncomfortable calculations of modern cosmologists, that the answer is not metaphysical. It's physical. It's thermodynamic. Time feels like it flows forward because entropy increases. Entropy increases because there are incomparably more high entropy states than low entropy states. And entropy started low because the Big Bang, for reasons we don't fully understand, began our universe in a state of staggering, improbable order. Your memories point to the past because your brain is a physical record-keeping device. And physical records can only be made of low entropy past states, not high entropy future ones. Your sense of causation of events preceding their effects is the felt experience of entropy increasing in your local environment. Your death, eventual and certain, is entropy winning. And consciousness itself, the very fact that there's a you here to be troubled by these questions, is a thermodynamic phenomenon, possible only because we live in a non-equilibrium universe still working through the consequences of an unlikely beginning. Now, I want to say something about the nature of understanding, because I think it's important, and because I've spent my whole life trying to understand things and sometimes failing. When you really understand something in physics, when you get it in your bones, not just as a formula, but as a way of seeing something interesting happens, the thing stops being mysterious in the old way. The mystery doesn't disappear, but it changes quality. When you didn't understand entropy, the mystery of time was sort of foggy and unapproachable. You knew time was weird, but you couldn't say exactly how weird. When you understand entropy, the mystery of time becomes precise. You know exactly where the mystery lives. The mystery is, why was the Big Bang low entropy? That is the question. Not, why does time flow? That's answered. But why was there a beginning at all? And why was it orderly? That's progress. Real progress. Moving from vague mystery to precise mystery is one of the most important things science does. And here's where I'll confess something to you. I find this entire situation breathtaking, not just intellectually, aesthetically. The fact that something as intimate and subjective as your experience of time is grounded in something as abstract and mathematical as the counting of microscopic arrangements, that's the kind of thing that makes me want to grab strangers on the street and tell them what physics has found out. The subjective and the objective aren't different realms. They're connected at the roots. Your innermost experience of being a temporal creature, of moving through moments, of having a past and facing a future, that experience is what it feels like. From the inside, to be a complex physical system in a universe where entropy is increasing. Not analogous to it, not correlated with it. The same thing, seen from different perspectives. Let me give you the most mind-bending version of this I know. Suppose, just suppose, the universe were somehow in exact thermal equilibrium, maximum entropy, no gradients anywhere, perfect disorder. Would time exist? Would there be a past and a future? In some mathematical sense, yes, you could still define a time coordinate in your equations, but would there be any physical difference between one moment and the next? No, nothing would be changing. There would be no records, no memories, no cause and effect chains. There would be no clocks, because all clocks work by exploiting entropy differences. There would be no observers, because all observers are entropy gradient exploiters. In a maximum entropy universe, time would be physically inert. It would exist mathematically, but mean nothing physically. Nothing would distinguish the future from the past, because nothing would be happening. There would be no arrow, no direction, no flow. The universe's non-equilibrium state, its improbable, precious, low entropy past, is not just the source of interesting physics. It's the source of time itself as a physically meaningful quantity. Without entropy gradient, time is just a coordinate. With entropy gradient, with the specific thermodynamic history our universe happens to have, time becomes the overwhelming, inescapable, intimate dimension of experience that it is. You exist in time. You are temporal. And that temporality, your past, your memories, your anticipations, Your sense of moving forward is the universe's specific thermodynamic history expressing itself through a complex physical system. You are the universe experiencing its own entropy increase. Think about that the next time you feel time slipping by. That slight wistfulness, you feel that sense of moments passing, of the present becoming the past, of the irreversibility of life. That is entropy. That is physics. That is the most fundamental law of nature playing out in the most intimate possible way. And here's my final thought, my final, stubborn, deeply held conviction. The fact that we can understand this, that we can sit here, these temporary arrangements of atoms that entropy will eventually dissolve, and figure out the thermodynamic basis of our own temperature.